So now we're going to shift to the topic of random or probability sampling. Those concepts mean the same thing, but this is a really important topic in modern research because the invention of random sampling really has allowed researchers to do a much better job of representing large populations, mass societies, with the tools of research. So the contribution of random sampling has been very large and widespread. So it's the foundation for around the world for most government statistics and also intergovernmental UN or World Bank statistics, such as statistics on unemployment or air quality, housing, family structure, all kinds of economic activity, business surveys, um, surveys of institutions of all kinds, and so most of the what are called official statistics, the statistics that governments produce all around the world, um, are based on random sampling. So random sampling really ushered in sort of the sort of the modern age of official statistics, and roughly this is sort of in the period after World War II. Random sampling was invented around the time of before World War II and a little bit later, but it didn't really take hold as an established practice until the 50s and even the 60s. So it's a relatively recent invention in the sense of um, only about a half century old, and so there aren't really many official statistics that go back before that. It's also the basis of major social surveys and of public opinion research. So random sampling has allowed all kinds of surveys to be done of mass society, mass opinion, voter behavior, attitudes about social issues, leisure behavior, leisure habits, all kinds of market surveys and consumer surveys that are representative of large populations based on relatively small random samples. And then finally, random sampling is important because it has a basis and it provides the basis for statistical inference. There are formal methods for assessing how precise a quantitative result is. There are formal methods for doing inference to a population and for testing hypotheses. And so we'll go into that a little bit here in this week, but we're not. This is not a course on statistics, but many of you have had a course on statistics, and this can give you a better sense of why, sort of um, the sort of the conceptual basis of those more formal mathematical procedures that you would learn in a statistics class. Now, to begin with, it's important to distinguish random sampling from randomized experiments. They sound similar, and even experienced people mix up the two ideas. So let's be clear about it. We're talking here about random sampling, which is selecting elements from a population in order to make an inference describing the population. So remember that diagram where so we're drawing people or selecting people from a big population in order to collect data on those people and then make an inference back to the population. Now, we select those people using random sampling. We select them at random, right, from the big population. Now, that's different from a randomized experiment, which we'll talk about in a few weeks. But a randomized experiment takes people or other units and uses randomization to put them into a treatment group or a control group. Um, it assigns people or elements to conditions or treatments in order to test causal relationships. And just to give it say a little bit more about this. So random sampling is often used simply to describe populations. It doesn't typically result in very strong causal evidence. Yet it does a really good job of representing or generalizing to a broad population. Random experiments often don't don't involve random samples. They involve volunteers, people who are or a convenience sample, and the randomization is used to give strong causal evidence. So a typical randomized experiment may have sort of less generalizability, a more local voluntary population, and yet the treatments are randomized. So there, it's very good causal evidence. That's the randomized experiment. But in random sampling, the people are drawn from a population, and so the conclusions are very strong about describing that population, although often the cause-effect evidence is not as strong in random sampling. But we'll talk about causation and experiments again in a couple weeks, and that distinction will be clearer then. Okay, so we'll start with simple random sampling. The basic model of random sampling is like selecting marbles from a jar or selecting numbers from a hat, and that kind of sampling is referred to as simple random sampling. So you select people or elements from a population so that each individual has an equal chance or probability of selection. So it's abbreviated as SRS. SRS, or simple random sampling, is the sort of the basic basic model of sampling for most statistical formulas that you would learn in a basic statistics class. But it's important to point out that even though it's a sort of the pure form of sampling that goes into many formulas, in the real world, random sampling often needs to be more complex than simple random sampling. Not because researchers want to make it more complex, just because to do sampling in the real world, you have to introduce certain kinds of complexities sometimes. So sometimes the formulas that you may learn in an introductory statistics class may need to be modified with the kind of real-world random sampling that we'll talk about a bit later. There are different types, like stratified sampling or cluster sampling or multi-stage sampling. That's the sort of thing that makes it complex. So earlier I said that random sampling was important because it provided a foundation for statistical inference. Now this is a big topic, and of course in statistics we would spend several weeks just kind of going over these ideas. But let me try to provide it in a kind of a nutshell and give you more of an intuition and a refresher on these ideas. But they're complicated ideas, so it's good in a course like this to kind of review the logic behind random sampling and how it provides an ability to make a formal inference about the population. Now, much of this rests on the notion of what's called the sampling distribution. Now, a sampling distribution is, if you can imagine, sort of, in any one study, you have a sample and you have a result from that sample, right? Like you sample a labor force and you calculate the unemployment rate. Now, that's one statistic from one sample. Now, one way to judge that statistic is to imagine what it looks like against the backdrop of many, many results from many random samples drawn the same way from the same population. And that pattern of many, many results is the sampling distribution. So it's a distribution of estimates from many samples of the same size, drawn from the same population. And it turns out that distribution follows a pattern called the normal distribution. It tends to be clustered in the center with tails off to the side. It's symmetrical, at least with a big enough sample. But even samples of 100 or so tend to form a normal distribution. Now, what's important about that is the normal distribution has certain characteristics to it. It's symmetrical. It's got a center, and by the way, the center happens to line up with the population characteristic that we're trying to estimate in the first place. So, but I'll say a bit more about that later. But it has a spread to it. The distribution has a spread to it. It's spread out, and the measurement of that spread is referred to as the standard error. Now, the standard error is the same thing as a standard deviation, right? In a regular sampling distribution. So the standard error is really just the standard deviation of the sampling distribution. But it has a different meaning because in this case it measures the precision, or rather the lack of sampling error, in a given estimate. So it's easier to look at a diagram and see this. So this comes from the book, figure 5.4, and it shows the idea of a sampling distribution. So here's how it works. Here's our one sample result, right? And we don't, by the way, this graph shows it being in one particular location, but we really don't know where it is in this distribution, right? But we're showing it here as being located right about there. But in the real world, we have one sample and one result, and we're not quite sure within the distribution where it falls. But still, we can imagine that there is this distribution out there. Our sample is one of the ones that we might have gotten because we drew it by chance, by random sampling, and it would be one of these results. Now, some of these results are high and some of these results are low, and they form a distribution, and they cluster in the center. And by the way, as I started to mention, the center of that distribution is the true population parameter, it's called, the characteristic we're aiming to measure with the sample to begin with. So if we're talking about unemployment in a labor force, the center of this distribution would line up with the real unemployment rate of the population if we had data on everybody. But any one of our random samples will differ from that real unemployment rate just by the luck of the draw, and some will be low, some will be high. They spread out around the true value, and they spread out in a way that takes this shape of a normal distribution. Now, the normal distribution has a center, but it also has a spread to it, and that spread to it is, if it were a regular distribution of scores or numbers, it would be referred to as the standard deviation, but in sampling statistics, it's referred to as a standard error. But it has a certain pattern, because the standard error, turns out within two standard errors, 95% of the scores would fall within two standard errors. So in a sampling distribution, 95% of the samples would fall within two standard errors of the center of the distribution. And so that pattern, which is typical of all normal distributions, that pattern allows us to make use of the standard error to put a boundary around our sample statistic, which is what becomes the confidence interval. So a confidence interval is it's also referred to as a margin of error. It's a boundary around the statistic, the result of our sample. It's a boundary around, let's say, the 5.5% that comes from our sample, that represents the chance or the confidence we have that the real unemployment rate lies within that interval. So it is what, margin of error is a good word. It's a margin of error around the results of our survey, which tell us where, at least with a certain level of confidence, where we think that the true level would be. So it provides a formal statement about the precision of our estimate that comes from one sample. Now, to calculate the confidence interval, at least at the 95% level of confidence, it's called, we use that rule I just mentioned of two standard errors, which represents the 95% of the distribution. It turns out to be 1.96 exactly, but thinking of two is pretty close, right? It's a pretty close to two standard deviations. Okay, so there's more in the book about the meaning of this and the way to calculate it. There's stuff in the sampling chapter, but also chapter 9, I believe, which is on making sense of inferential statistic, provides a bit of an overview as well.